Today we're going to talk about René Descartes' rules of signs. By signs, what I'm referring to are positive or negative signs. So, his first rule, the real rule, is the number of positive real roots of a polynomial is equal to the number of consecutive sign changes reduced by any multiple of 2. So, let's break down the different pieces of what this is saying. Positive real roots. So this counts for all real roots, but only the positive ones. When I talk about consecutive sign changes, I'm talking about, say, plus, minus, plus, plus. This is one sign change, a second sign change, so that would be 2 sign changes. So that's saying that the number of positive real roots is 2, except it says reduced by any multiple of 2. So it would be 2 or 0. It could be reduced. It could be just 2, or it could be 2 reduced by 2, which would be 0. If I gave you a long list of positive and negative signs, we could say, okay, there's 1, 2, 3, 4, 5 consecutive sign changes. So there could be 5 positive real roots. There could be 3 positive real roots, or there could be 1. We can't have negative numbers of roots. So that's why I would say 5, 3, or 1 positive real root. It's a weird thing, but this in combination with the rational root test will allow us to focus our energies on the roots that are actually promising. So how many positive zeros do each of these have? So this has 1 sign change, positive to negative. So that's 1. How many does this have? This is going from positive to negative once, and this is going from negative to positive, so that's 2, or it could have 0. This is going from positive to negative, negative to positive, positive to negative, so that's 3, or we could reduce it by 2, 1. And these are all positive, so it has 0 positive zeros, positive real zeros. So that's what I mean. Just count the number of sign changes, and if it's 2 or larger, then you can subtract 2 as many times until you get to 0 or 1. The number of negative real roots of a polynomial is equal to the number of consecutive sign changes after replacing x with negative x, reduced by any multiple of 2. So this is talking about how if we have a polynomial, whatever's happening over here, we can reflect it over to the other side by turning x into negative x, and then we can use the rule on the right side. So we're going to replace each of the x's with negative x, and then apply the old rule. So here, if we replace x with negative x, and we raised it to the 6th power, we would have 64x to the 6th again. So this is still going to be 1, 1, negative 0. Here, if we replaced x to the 4th with negative x, it would be negative x times negative x times negative x times negative x. So this would be x to the 4th again. X squared would be negative x times negative x, so that would be x squared again. So this is still just 1, 2 sign changes. So this could be 2 or 0 negative zeros. In this problem, when we plug in negative x, all of the odd exponents are going to change. So this would, if we plugged in f of negative x for this third one, f of negative x equals negative 2x cubed minus 5x squared minus 4x minus 1. So the terms with even exponents didn't change at all, but the terms with odd exponents, 4x and 2x cubed, did change, so that now they're negative. Now all of the terms are negative, so how many sign changes are there? There are no sign changes. This last one, if we put in negatives for negative x for this, then we get 2x cubed, well, negative 2x cubed, because that's an odd exponent. That is, the negative x squared is still x squared. And when we replace x with negative x, 10x becomes negative 10x. So this has 1, 2 sign changes. So there are 2 or 0 negative exponents. Oh, sorry, negative zeros. So the first one has 1 positive 0 and 1 negative 0. The second one has 2 or 0 positive zeros and 2 or 0 negative zeros. The third one has 3 or 1 positive zeros but doesn't have any negative zeros. And the fourth one has no positive zeros but could have 2 or 0 negative zeros. So that's Descartes' rule of signs.